Hi, I'm Ryan. Welcome to another exciting episode of Check It Out. Today, we're going to be discussing superluminal communication, or whether or not we have what it takes to communicate with the heavens.
Check it out!
But before we can even imagine faster than light communication, we're going to need to learn a thing or two. Alrighty, now what exactly is the speed of light? According to the theory of special relativity, the speed of light is the maximum speed at which any particle in the universe can travel. This is around 3 times 10 to the 8 meters per second. That's 3 with 8 zeros behind it. This universal speed limit is defined as the speed at which massless particles that don't actually weigh anything, travel through the vacuum of space. These massless particles are known as electromagnetic radiation, or particles that radiate electromagnetic energy. For example, the lights in your house. Pretty neat, huh? Alright, the coolest thing about the speed of light is that it is constant, regardless of the inertial reference frame of the observer. That is, where you, the stationary person, are viewing an event to occur. Alright, let's say you have a train moving along at nearly the speed of light. That's around 186,000 miles every second. In the center of this train, you have a firecracker, and Mary Jo in the train looking at the firecracker. On the edge of the tracks, you have Thad looking at the train. As the train passes by, the firecracker goes off. What do you think happens? So, according to Thad, the light from the firecracker is going to hit the back of the train before it hits the front of the train. That's because the light from the firecracker is going to catch up with the back as the front moves away from it. But think about Mary Jo. She's inside the train. Nothing is moving. She's in an inertial reference frame with respect to the train. So, according to her, the light is going to hit the front and the back at the same time. Wait, what just happened? Well, according to special relativity, both things happened at the same time. According to Thad, who's standing outside the train, both the train and the light are moving. But, according to Mary Jo, who's in the train, moving at the train's speed, only the light was moving. Wacky stuff. Well, we now know what and how this universal speed limit of light works. So where do we go from here? Before we talk about faster than light communication, we need to figure out if it's even possible to go faster than the speed of light. Alright, so our first experiment is going to have to do with the Cherenkov effect, or light attempting to pass through something that is denser than Alright, so our first experiment has to do with the Cherenkov effect, or light attempting to pass through something that is denser than the vacuum of space, something that has little tiny particles floating around in it that the light has to pass through, such as this jello. Now, as light attempts to pass through the jello, it is slowed down and is slightly bent, or rather it experiences a larger index of refraction than if it were to just go through the vacuum of space. So essentially, didn't we just slow down this universal speed limit of light? Well, how does this help us at all? Well, there's an experiment that can be done where we give the light about to enter the jello a little bit more energy, so that when it actually passes through the jello, we're actually moving faster than the speed limit says it should be. So, did we just go faster than the speed of light? So, as it turns out, we didn't actually go faster than the speed of light. We only went faster than light normally wants to go inside of the jello. We're still limited by this 300 million meters per second speed limit, no matter how much extra energy we give the light. Ah, shucks. It was a good try. Alright, well, if we can't speed light up or make it travel any faster, then what else can we do to travel faster than the speed of light? Alright, let's shine a light on a dark wall and put your finger in front of it so that your finger casts a shadow in this wall. Now, if you were to move your finger fast, notice that your shadow would actually be moving further than your finger does in the same amount of time. What if we took a light and we shined it on the moon, a much larger and further away object, and then you cast a shadow with your finger on the moon? Well, you wouldn't have to move your finger super fast to get the shadow moving across the moon to move faster than the speed of light. Wait, what just happened? Now, you might be thinking that since we've moved this shadow faster than the speed of light, that we've somehow broken this unbreakable speed limit, but not so fast. So, in order to explain this, we need to think about what a shadow actually is. Most people think that a shadow is just a bunch of darkness surrounded by light. But what is this absence of light? In fact, this darkness is merely a spot where the light is not, or where it has no information in it. So, even if you move this space of no information back and forth really, really fast, the light around it isn't moving any faster or slower than it should. One more time. Alright. This is because light can only travel so fast, meaning it's going to take a certain amount of time for this light to reach the moon. So the light surrounding your shadow is going to be moving like a wave towards the moon, only at its governed speed limit. Sort of like a wave traveling down a string. So even though we might have thought we've made like a revolutionary discovery, we've only been misinterpreting what is actually happening. Alright. By now you're probably thinking, is it possible to communicate faster than the speed of light? Technically so far we haven't been able to prove that faster than light communication is even possible, but we do have some very smart people looking into it. One of the biggest theories right now is called quantum entanglement. I know, it sounds complicated, but let's give it a shot. Alrighty, in quantum mechanics, we break particles down into their tiniest components, which makes some really weird stuff start to happen. Let's say that we're creating two particles. One is going to be a square, and the other one has to be a circle, with them both having the same probability of being either. Now, if these particles are entangled, when one is measured to be a square, the other one has to be a circle. The only problem being is that we don't know what one will be until we measure the other. And until then, they're going to have the same probability of being either. The craziest part is that it doesn't actually matter how far apart these particles are. When one is measured to be a square, the other one has to be a circle. Pretty cool, huh? Alright, this may sound confusing, but it's important in determining our next idea for faster than light communication. Let's say we have our two entangled particles, one a square and one a circle, but we don't know which one is which yet. Let's say we keep one of the particles here on Earth, but we shoot the other particle off into space at the speed of light. Now let's say that we will read this particle as being a square as soon as it hits, say, something like a star. Well, due to our theory of quantum entanglement, our other particles should read as a circle instantly, thus traveling the information faster than the speed of light. Alright, hold up one second. We actually broke a fundamental law of quantum entanglement in this experiment. By telling the particle out in space to read a square if something happened, we forced its outcome to be a square. This breaks the fundamental law of quantum entanglement, meaning that the particle still on Earth actually has an equal probability of reading either a square or a circle. We corrupted its information in a way by telling it what it has to be. Quantum entanglement really only works if you have a random outcome of either event occurring. Bummer. There are a few other theories out there revolving around superluminal communication, or faster than light travel. These theories involve crazy particles called tachyons, scary wormholes, or even wrapping the fabric of space-time around yourself. Unfortunately, we're out of time today, and we'll have to explore these other theories in a later episode. But in the meantime, grab yourself a flashlight, go outside at night, and see if you can't create a faster than light shadow on the moon.
Check it out.
Yes, okay. I think we're good.